I left off saying that how many astronomical events had to happen in outer space, and how many astronomical events had to happen on Earth for you to get here. Just going back, I did mention that light is constant, 10 to the minus 10 centimeters per second, and that they knew that by measuring light coming from, I said star, but I meant to say planet. So light coming from a planet towards you, and then measure the light after the planet went by you, and it's exactly the same as constant. I also said that I was going to tell you what's happened at 10 to the minus 12 seconds. So besides getting all your particles and antiparticles that come together and annihilate each other, you also get your electromagnetic force. And the electromagnetic force, that's the one that keeps you from falling through the earth to the center of the earth. But you also get your fourth force, the weak force. Now, if you're in that room and you're not noticed, well, maybe you should be noticed, because you radiate. You're a radiant person. Not that much radiant, so nothing you could probably measure, because it takes millions of years times the age of the universe for you to show your radius, for your protons to radiate away through radioactive decay caused by the weak force. It's nevertheless important to you. You'd probably die without it, because it keeps the center of the earth, which is molten iron, keeps it molten through radioactive decay. And when the earth rotates around its axis once a day, it sets up an electromagnetic field or shield around the earth. That's why you get your magnetic north pole and your magnetic south pole. And that protects you from harmful solar radiation from the sun and harmful cosmic radiation from outer space. It also protects the atmosphere from being blown away by solar radiation. And the atmosphere is important for you because you like to breathe air, oxygen. And it mitigates things coming down from space and hitting you or causing a lot of commotion. Meteorites, meteors, asteroids, and comets. And I say mitigates, it usually burns up most of them in the atmosphere, and those that come through are usually made so small they're not that harmful. It does let a few big ones through as well, very infrequently. You get more asteroids coming towards Earth every 30 million years, so it's quite a rare event that you would get large asteroids coming through the atmosphere. Nevertheless, it has happened. So let the force be with you. Now, we have shown perhaps how you got all your atoms, what you are. But where are you? Where are you located in the universe? What part of space do you occupy? Well, I guess if you're taller, you'd occupy more space than if you're shorter. And there's some advantages of being taller, like Eisner is 2 meters tall. He's got the most consistent fast serve in tennis. Roddick is another fast server. He's 6'5". But supposing he wanted to appear to be more average, quote, normal, then you measure yourself in larger units of measurement. So Eisner, rather than say he's 2 meters tall, he could say he's 2/1000ths of a kilometer high. Or use a bigger distance, say the distance between here and the moon, and that's 400,000 kilometers. Or the distance to the sun, 150 million kilometers. Or to Pluto, 19 billion I think it's 19 billion kilometers away. Or the nearest star. That would be something like 400 times, 4 times 10 to the 13th kilometers away. Nearest, and so on. So when we get to those large units of measurement, we have to figure out another unit of measurement. Now, when you're in that room, and you finally get to see somebody, and you ask them, well, how's it going? How are you doing? And you probably want to know how he's doing at that time. You never will. Because you're looking at him in the past. The time the light has come to travel and hit you. Billions and trillions and quadrillions of Planck times ago. So you never see things as they are, but things as they were when the light left them to reach you. So rather than say the moon is 400,000 kilometers away, we can say it's 1.2 light seconds away, because it takes light that long for it to come from the moon to see you. So you can see it, rather. So you don't see the moon as it is now, you see it as it was about 1.2 seconds ago. So we call that distance 1.2 light seconds. Same with the sun, we don't see that. You don't see that as it is now, but as it was 8 minutes ago. So that distance is 8 light minutes. Pluto, we see it as it was 5.5 light hours ago. And, okay, the largest, the nearest star, Proxima Centauri, we see it as it was 4.2 light years ago. And the nearest large galaxy, Andromeda, 2.9 billion light years. The farthest galaxy, 15 billion light years. The farthest star that we see through the Hubble telescope is 13 billion light years away. So Eisner occupies only a very small fraction of space. Supposing you wanted to, you're small, and there are advantages of being small. Gymnasts are usually smaller. Jockeys for sure. But if you want to appear average or more normal, you measure yourself in smaller units of time. Smaller units. So rather than say, well, I'm 1 meter, you can say you're 100 centimeters, 1,000 millimeters, 1,000,000 micrometers, or going back to the smallest units of measurement that you can get, it's called a Planck length. And the Planck time is the time it takes light to travel 1 Planck length. And 1 Planck length is 1.6 times 10 to the minus 35 meters. So where are you in space? Between 1 Planck length, which is 1.6 times 10 to the minus 35, and 13 billion light years. You don't occupy much of space at all. Now the other thing that, a physical attribute that you have, well, you're attractive. So again, maybe you should be noticed, because you are attractive. Well, you say, well, maybe not at a distance. I may look somewhat attractive, but when you get closer, you'll see that I'm overweight or get flaws. It's the other way around. The closer you are, And the bigger or fatter you are, the more attractive you are. Newton, back in the 1600s, he saw that the apple fell from the orchard outside of his house to the ground. Didn't hit him on the head, as some people want to think, but it just fell down from the tree down to the ground. And he said there's an attraction between the apple and the earth. He went on even to form a law or an equation to show that, to show how it happens. He says it's proportional, or if you like, it's equal. Just add a constant to make it an equation. It's equal to the mass of the apple, the amount of material it has, times the mass of the earth, amount of material of the earth, divided by the distance between the center of the apple and the center of earth, squared. And what do we call that? Gravity. So he's given us the force of gravity. That's the force of gravity. But he also said that that's also between any two objects. So you're in that room, and your attraction to the other person in the room is equal to his mass times your mass, divided by the distance between you two, squared. Newton also said that if something is moving, it'll keep moving unless something stops it. Aristotle said 2,000 years ago, no, everything will grind to a halt. What keeps it moving, even if you like, is the hand of God. For instance, why does the moon go around the earth? Well, Newton says it's his two laws. And to use a thought experiment, take a cannonball and a cannon up to the top of the mountain, drop the cannonball, and it drops to the mountaintop, just like the apple drops to the earth below. Shoot the cannonball out of the cannon. In other words, give it some momentum or some speed. Momentum is just your mass times your speed or velocity. And it'll go mile, kilometer, or kilometer before it drops. Shoot it harder, and it'll go all the way around the earth, halfway around the earth before it falls. Harder again, all the way around the earth before it falls. Harder again, it'll keep going around the earth. Don't shoot it faster than 25,000 miles per hour. It'll go way into outer space. So it's the force of gravity and momentum that keeps the moon going around the earth, and the earth going around the sun. But I might have misled you again. You're not only a little bit attractive, you're no attractive at all. You form a warp around you. You change the space around you, and the other person falls into that space. Not because he's attracted to you, but the space around you has changed. Like you stand on the trampoline, you form a well around you, or indentation in the trampoline, and put a basketball on it, and it falls towards you. The closer it gets, the harder it falls. So the attraction is not, as Newton said, or the gravity is not, as Newton said, attraction between two masses. It's a warp in space-time. Einstein's general theory of relativity. Now, what does that mean? He came up with that with a thought experiment, so it's really a hypothesis at that time. And, of course, many scientists, journalists said, well, we've interviewed all these scientists, and they can't agree with that. They're skeptical. What did Einstein say? Well, all you need is one scientist and one piece of evidence to prove it's wrong. And then I'll say it's wrong. To get an idea, here's another thought experiment then. Take a rubber sheet representing the Earth, space-time, or let's say space for now. Stretch it out, and take two ball bearings, one bigger than the other, one a bigger one representing the Earth, the other smaller one representing the Moon. Place the larger ball bearing on the rubber sheet, and it forms an indentation or well around the ball bearing. Or the Earth forms a warp in space around the Earth. Then roll the other ball bearing across the rubber sheet, and depending on how massive each is, how close you come to the object comes to the other object, or how fast it's going, it'll either go right by or hit the warp in the case of the Moon, or the well in the case of the ball bearing, and be deflected and go on its way. Or it'll hit the well or the warp and go around inside of that warp. So it's not because there's an attraction between the Moon and the Earth, it's because the mass of the Earth forms a warp around space, and the Moon falls into that and goes around. Now that is a hypothesis then. What's the empirical evidence? Well, they did. They took it back into the lab to do an experiment. And the lab they used was a solar system. They waited for the sun to eclipse, solar eclipse, and looked at the stars beyond the star, beyond the sun. And they found that the stars behind it had been misplaced. So what had happened there is the photon of light hit the warp caused by the mass of the sun and was deflected so that the stars appeared in a different location. And Einstein became very famous. And really, there's no evidence to dispute that, even though it's rather a strange idea that space changes, and you can go around changing space. You also change time. So gravity is also it's a warp in space and time. So as you approach a mass, the time slows down. Now, Einstein's laws, going around changing time and space, what do you need that for? I can do without that. I'll use Newton's laws. And people do use Newton's laws because they're much easier to use. And for all many practical purposes, they do fine. They're really a subset of Einstein's laws because you can derive Newton's laws from Einstein's laws. However, if you want to find out how Mercury goes around the sun, Mercury's closer to the sun than the other planets, and it's more affected by the warp caused by the mass of the sun. So you need to use Einstein's laws to more definitively define the orbit of Mercury. Also, if you want to go on a trip and use your GPS, you better incorporate Einstein's laws. Because your GPS would be out in 2 hours if you didn't. Because time on the satellite runs faster than time on the Earth. That sounds kind of crazy. You need an atomic clock to measure it, but it does. And and because the GPS uses triangulates on distance from the stars, from the satellites. Your GPS would be out in 2 hours if you didn't incorporate that difference of time. And, as I say, there's been no evidence ever to dispute Einstein's law of general relativity. So it really defines the universe, how it works, with things with mass. It's a, if you like, an Einsteinian universe or Einsteinian world vision. Did he get a Nobel Prize for that? No. But he did get a Nobel Prize for the other world vision, which is that world with a very small, which doesn't care about the force of gravity or mass, because when a mass is so small and the force of gravity is so weak, you can ignore the force of gravity, which is done pretty well in quantum mechanics and quantum field theory. Except when you can't do that. But for many practical purposes you can. And quantum mechanics is like the Einstein universe. Is a very useful tool for scientists. And they have not found any evidence that does not agree with all their equations that they get from quantum mechanics and quantum field theory. But Einstein didn't like the other vision. He spent the rest of his career, most of his career, trying to incorporate the two world visions together. Quantum gravity, if you like, or a theory of everything. The founders of quantum mechanics, one of the founders, of course, is Planck. He said that both space and time are discontinuous. It's the smallest unit of each one. The other reason Einstein didn't like the quantum mechanics is because it uses probabilities. Nothing is definite. It's just a probability. You have to add up the probabilities to get anything like we look at with mass in our world. Heisenberg was another founder. He said if two things are related, then the more you're trying to find out about the one, the less you'll know about the other. For instance, if you want to know the speed and location of a particle, the more you define the speed, the less you'll know its location, and vice versa. Not because there's a difficulty in measurement, but that's the reality in the quantum world. To show the weirdness, the classic experiment is a double slit experiment. You pass light through two slits, and you see what happens to the other side on the wall or a screen. You'd probably think that you'd get two lines. One where it goes through the left, another where it goes through the right. No, you get several lines. Because as I mentioned before, light can both be a particle and a wave. When it goes through the two slits, the waves interfere with each other and form the several interference lines, like you get when you throw two rocks in a pool. But if you observe the light before it goes through, just look at it. What happens is you get the two lines rather than the several interference lines. So by looking at light, it changes from a wave into a particle. Okay, then let's just release one particle, one photon at a time. Then surely it either has to go through the left or it has to go through the right. And over time it will build up a left line and a right line. No. Interference lines. Okay, let's look at one particle at a time. And lo and behold, it changes from interference lines to two lines, one left, one right. So how can it go through both slits at the same time? how can it interfere with itself? And by looking at it, how can it not interfere with itself? Just by merely looking at it. Now here's again where you might want to, and another person who was a founder, I think it was Feynman. Yeah, Feynman. He said anyone that understands quantum mechanics doesn't understand quantum mechanics. It's so weird. And yet, as I say, it's the most accurate tool that scientists have, and there's no evidence to ever dispute it. Look where things out to 23 decimal places. So here we have two different world visions. Science has two different world visions which are incompatible. So does it really know what's going on? Quantum mechanics and quantum field theory. Oh, by the way, with quantum field theory, saying that everything changes starts off as a wave, it changes into a particle. That's, photons and electrons, etc. So maybe here's where we need to again turn to religion, because most religions say, well, there's someone up there watching over everything to make sure it's working. Well, that's what science is saying too, really. So the only time that science gets into trouble with that, because they both work fine, even though they're totally incompatible. As I say, one has probabilities, the other doesn't. The one has small uses of time and space. Space and time is discontinuous. In Einstein's world, it is not. In one world, you have to incorporate space. And you have to incorporate mass. In Einstein's world, it's one of the foundations of the world. Whereas in quantum mechanics, you ignore gravity and mass. Except when you can't, and that's when you have a mass that is both small and dense. Like in a black hole or at the beginning of the universe. So there's been things, scientists, mainly theoretical scientists, like Einstein, is trying to come up with, combine the two theories to a theory of everything, or theory of quantum gravity. It's very mathematical, because one of the latest ideas is what they call string theory. It's really a string hypothesis, because you really can't find empirical evidence to support it, saying that all matter is and forces are made up of strings, very small, billions and billions times smaller than quarks. So it's very hard to measure them because you can't, they're so small. And also the other thing they need is to have more than 3 spatial dimensions, 10 spatial dimensions. And as far as I know, there's no one that's gone into the other dimensions and come back. But Matthew do it, but not in real life. So it's a highly mathematical or theoretical. Nevertheless, there's a lot of scientists, brilliant scientists, working on it. So here's another area that science doesn't really know what's going on in the fundamental level, and for how you got here.